Hello class, my name is Joseph Morales and I will be doing a video presentation on kinetics of particles in the normal and tangential coordinate system. This is obviously the video option because I'd rather do a video than have to write a 12-page paper. Okay, now before I talk about my subject, I want to briefly discuss kinematics as opposed to kinetics. Well, the differences between the two of them. Because sometimes it could be a little bit confusing, as it was for me in the beginning. Now, if I'm talking about kinematics, in simple terms, it is defined as why a particle moves, which would be the motion of the object, a particle's position, velocity, and acceleration. Take, for instance, this train here. This train is moving according to the graph to its position, which means, for example, in 30 seconds, this train would have moved 360 meters in 30 seconds. Likewise, we can get the velocity from the position here. The velocity is increasing, but here it's remaining constant. Same can be said about the acceleration. Here the velocity is increasing, so here we do have an acceleration, but here the velocity is constant and the acceleration would be zero when it's constant. That is kinematics in easy short terms. Now kinetics. In contrast, kinetics is why particles move. And they move because of the forces acting on the body. Here I'm going to take this example of this train here. Okay, draw a rectangular coordinate system. Here y and x along this direction. My voice cracked. Okay, now in this train we could point out the forces acting upon it. And just, for example, we're just going to say we have a force pointing forward, making the train go its direction. That will be, and then force is mass times acceleration, because it has to move some way. And then obvious forces like the normal force and the force of the weight. Now, this is what I would define kinetics. The forces acting on a particle. For this example, the train is moving in a straight direction, we're going to assume. So analyzing the forces would be easy, because we could just use a normal rectangular coordinate system. But what if you're moving along a curvilinear path? For, say, a roller coaster, for example. And you wanted to analyze the cart or the roller coaster here, here, or maybe even here. Now, doing this in rectangular coordinates would be pretty hard. It would just be a headache, I would say. So what if we could analyze the roller coaster anywhere along, or the cart anywhere along this roller coaster? Having the cart as a frame of reference. So wouldn't it be easier? Obviously, this would depend on factors such as the radius, the velocity, the accelerations in those directions, and so on, which I'm going to discuss later on in this video. But wouldn't it just be easier in general? Now, this brings me to my introduction of kinetics of particles and the normal and tangential coordinates. I just talk about kinetics of particles in the normal and tangential coordinates because they oftentimes make it easier to analyze forces of particles when curvilinear motion is involved. And the good thing is they could be analyzed along anywhere the particle travels. Yeah, I'm going to show that a little bit better here, just to see things visually. This particle can be analyzed anywhere along this curve with this new coordinate system. The coordinate system involving the normal and tangential directions is known as the oscillating plane, or the embracing plane. I hope I said either of those correctly. Now, in this coordinate system, the velocity will point in the tangential direction. It's important to note that the tangential direction points in the direction of motion, so I'm just going to write here. direction of motion. And the direction of motion follows the path where the particle travels along the curve. So the tangential direction is in charge of bringing this thing to complete its curvilinear course or whatnot. And the normal coordinate will go in the direction of the radius, right here. Whenever we have we're dealing with a curvilinear shape or plane of travel, then we're going to be faced with radius to encounter. Right here. Now, something different that differentiates this plane from a normal rectangular plane is that now we're going to have two accelerations. We're going to have an acceleration in the tangential and an acceleration in the normal direction. That means acceleration has two components: tangential and acceleration in the normal, right here. And here we have another visual that can better show that. I'm going to demonstrate the normal and tangential accelerations with an example. Say we have a ball attached to the end of this string here. Pretend there's something attached to it. And we're rotating this around a circle because we're spinning this. Now, we take the tennis ball. This tennis ball will have two kinds of acceleration: a tangential acceleration and a centripetal acceleration. See? Now, the tangential acceleration points along the tangential direction, and the tangential direction is the same direction as where the velocity goes. So we can state that there. Now, what differentiates these normal and tangential coordinate systems from a rectangular coordinate system is that now we have an acceleration pointing towards the center. And this acceleration points in the normal direction, along the normal. So you can call this the centripetal acceleration or the normal acceleration. This acceleration acts along the radius, also, because it's worth noting. So when we're spinning the ball will feel an acceleration towards the center. So we may not feel when we're spinning it, but the ball will feel the acceleration towards the center. Alright, here I provided some other visuals to kind of see other examples of the accelerations. Here we have a tangential acceleration. And I think this is something from NASA, like that simulates G-force or whatnot. I'm not too sure. But here's a tangential, and here's a normal pointing towards the center. We could easily find the forces along this thing here. This example is actually, I think, a bit more interesting because now we have different radiuses. And with the different radius, we're going to have different magnitudes of the normal and tangential accelerations. Here, you see this radius is different than this one. Now, so why do we have a normal acceleration in the first place? Or a centripetal one? Same thing. Well, let's find that out. Now I'm going to talk about how we get a centripetal acceleration pointing in the normal direction. Okay, here we have a particle, and the particle moves to this location, right here. It's also worth noting that the curve is bound by radius. There's going to be a radius along this entire curve moving. It moves here, that location. Now, this particle would have moved a distance ds over a time dt. It took a time to move from here to here. And that is known as the velocity, right there. Now, but what is this ds here? Okay, well, we do have a radius here, and the particle did move a distance d theta. So we could say the small ds is the radius times d theta. Why? Let's take that for example. Take this for example. It's failing. Almost got it. Okay, take the radius for example. It's moving a distance d theta, so it's multiplying by the entire d theta. That's easy to understand, I hope. Now, let's define this. Velocity is ds times d theta, and ds is the radius times d theta dt. Something I mentioned before is that the velocity goes in the tangential direction, the direction of motion. So there's going to be a velocity. Now this is how we obtain velocity. That's pretty straightforward. It's not too complicated. Now let's go into acceleration. The acceleration is going to be the derivative of the velocity with respect to time. D t. Okay. We're taking the derivative of the velocity, and don't forget the unit vector. Now this from calculus, this is the product rule. So we solve for one thing, and then we solve for another thing. So dv dt, the derivative of the velocity, and the unit vector comes along for the ride, plus the derivative of the unit vector, and the velocity comes for the ride. There. That is equal to the acceleration. There. Okay. So I just did math here, but how does this actually look like? Well, let me show you. Okay, got this here. Okay. So recall that we're gonna have a velocity vector. This is this velocity vector of the velocity we just found. Now the velocity is changing. There. That means there's gonna be a changing vector. Here. A changing tangential vector. As it says here. And don't forget the radius is going in the normal direction. Oops. There. And here. R d theta. Okay, so what is this saying? Well, first of all, pay attention here. The derivative of the velocity over time, no, dv over dt is equal to the acceleration. So right here, we already have the acceleration in the tangential direction. But this isn't so easy, because this vector is changing. This velocity is changing here. So we need to solve for this unit vector, for the change in this vector. Now we do that using vector math. We take this vector. Oops. We take this vector, include our normal vector in the normal direction, our normal unit vector, that is, right there. And we obviously have the displacement from the initial velocity vector to the changing velocity vector. Traveling a distance, this small distance here. Okay, we are eventually trying to solve for this in order to find our acceleration in the normal direction. So what you do here is you multiply d theta times the unit tangent vector right here. And I'm going to show that like that, this. Here, if you multiply it, it runs around d theta. The unit vector runs around d theta. Okay, that could be written here as the displacement times the unit vector of the velocity multiplied by d theta. Also, unit vectors are always equal to 1, so now this could be written this way now, with a 1 instead of the vector. Here's something that is important to notice, is that this displacement vector is going along the same direction as this unit vector in the normal direction. So now this could be written this way is d theta times a unit vector in the normal, right there, okay? And now I'm gonna compare and contrast this with the acceleration here. So we could see the similarities as to what is happening. And the velocity will also be useful for this. Okay? Now, if we divide both sides by dt, we are eventually going to solve for this portion here. So we're going to find out what this portion actually is. So, to help us do that, we could actually look at this equation right here. So, we want to solve for d theta over dt. Well, that's easy. We just move the radius over to this side. And at the end, it's going to be d theta over dt is going to be equal to the velocity over the radius. And that can be plugged in here. There. And so we are going to be left with displacement of the unit vector is equal to the velocity over the radius in the normal direction of the unit vector here. And this is plugged into here. There. So now we actually found our acceleration in the normal direction. So this could be written as here, dv dt in the tangential direction plus velocity squared over the radius in the normal direction. And we have now found the accelerations we so much wanted for, or so much longed for. Here's the one in the tangential and the acceleration in the normal. So now we actually know why there is acceleration in this direction and an acceleration in this direction. 18. Now that we know why there is a centripetal acceleration acting in the normal direction, we can find the forces acting on the particle, which moves along a fixed curve, or a fixed path, using the normal and tangential directions. Something to note here is that there is going to be no force moving along the binomial direction, because the particle is constrained to move along the fixed curve, and at no point is the particle detaching from the curve, or its path. So we call this zero. Force is equal to mass times acceleration. And because of this, the force is moving in the direction of the accelerations, as stated before, in the normal and in the tangential. Now, to find the forces acting on a particle along a curve, I draw a free body diagram using the normal and tangential coordinates, having the particle as frame of reference, in which there's going to be a force, a centripetal force acting in the normal direction, which is going along the radius. And there is a tangential force acting in the tangential direction, going in the direction of the velocity. And also the direction of motion. Tangential, the direction of motion, going along the motion, or along the curve here. Now, our equation of the motion would be force is equal to mass times acceleration. So here I'm just drawing a bunch of forces that I made up. Say there's a force here, there's a force here, and there is a force here. Now with all these forces acting along this particle, you must sum them in the normal and tangential directions. Oh, I had an image. Oh, here. Got it. Here, summing the forces in the tangential and the forces in the normal. Keeping into consideration that the force in the normal is going to have and acceleration dependent on the velocity and the radius in the normal direction. And this is how you find the forces acting along a particle moving along a curve. To better show this, I'm gonna provide an example problem, which I'm gonna do later on. Oop, forget the mess. Okay, now I'm gonna solve an example problem involving kinetics of particles in the normal and tangential directions. Now, why am I using the normal and tangential coordinate system? Because our guy here is undergoing a curvilinear motion. He's riding along this curve, and it's easier to analyze the forces when this happens in the normal and tangential directions, as I explained in the video. Now, this question reads, a man having a mass of 75 kilograms sits in the chair which is pin connected to the frame BC. If the man is always seated in an upright position, determine the horizontal and vertical reactions of the chair on the man at the instance theta is equal to 45 degrees. At this instance, he has the speed of 6 meters per second, which is increasing at 0.5 meters per second squared. Now, to write our knowns and explain as we go along. So, knowns. First of all, we have the mass, which is 75 kilograms. That happens at the angle 45 degrees. The radius of our frame B to C is 10 meters. And our velocity is 6 meters per second. Oh, don't forget the acceleration. That is 0.5 meters per second squared. Now, to explain these terms a little bit, all the actions or all the forces we need to find are going to happen at this angle, 45 degrees. We have the radius of our frame, and recall the velocity is pointing in the tangential direction, the direction of motion. And here it reads that our speed is increasing at 0.5 meters per second squared. This acceleration is corresponding to the tangential direction, so we could call this the tangential acceleration. Right there. And the question is asking us to find our reactions in the x and the y. So reactions in the x and reactions in the y. Right there. So if you don't know what those reactions are, I'm just going to explain them really quick. Here is the reaction in the x, and here is the reaction in the y. Now, what these reactions are, they are basically forces that the chair exerts on the man when this curvilinear motion is happening. That's an easy way to say this. So the question is asking us to find these reactions here. Now, to do that, or to begin doing that, I need to establish my coordinate system. Having our guy here as the frame of reference. And I'm going to draw the normal direction going this way. So why am I doing that? Because notice that the centripetal acceleration points towards the center here, the same direction as the radius of this frame right there. So this guy is going to feel a normal acceleration pointing this way. And that's why I draw my normal direction in the same direction. Then I have the tangential direction, which is perpendicular to the normal. I hope that's the correct term to use. Got my negative normal and at the negative tangential. Right. Okay, next we have to signal the forces happening on our guy on this coordinate axis. So that would simply be the reaction in the y, the reaction in the x, and the force of the weight. And the weight is mass times gravity, right there. Now the goal is to solve these forces in the normal and tangential components, because that's where everything happens upon, in the normal and tangential directions. But before, I do need to establish the angles here. This is 45 degrees, this angle is the same angle as this one here. And recall that for a right triangle, all sides must add up to be 180 degrees. This is going to be 45 degrees. I do want to bring your attention here for a moment to understand the angles a little bit better. Now from here to here we have 180 degrees. This displacement is 180 degrees, and obviously if you could do that again you're going to have 360, but this is 180. Now because this is 180, this half is going to be 90, and this half will also be 90. Meaning that if we have an angle that is 45 degrees here, this also has to be 45 degrees. Because 45 plus 45 is 90. And you could also say that if this happens here, this is also 45, and this is also 45. So I just want to establish that, because this case here is the same as this scenario, as what's happening here. So here we have 45 degrees. And for this entire coordinate system, it's all going to be 45 degrees. So nothing too complicated in that regard. So 45 degrees and 45 degrees for the weight. And also this makes sense because, as you can see here, this reaction in the x is pointing straight right in the middle, in between the tangential and the normal direction. Same as for the reaction in the y, and the reaction and the weight. I don't know why I called that a reaction, the force of the weight. They're pointing towards the middle. Now before I begin summing my components in the normal and tangential directions, I do need to establish the opposite and the adjacent sides of this triangle, so we could solve for our components. So for the reaction of the y, if I'm analyzing that with respect to this angle, I'm going to have to draw a line that is parallel to the tangential direction that goes in the same direction here. So this would be opposite, and this would be adjacent. Likewise, for my reaction in the x, I'm going to choose this way here. And notice how these blue dots are parallel to my normal direction. Alright, so the angle is going to be opposite, and this angle is going to be adjacent to it. And as for my weight, here I did the exact same thing. Here is the opposite. Okay, that's there. Okay, so now I've established my opposite and my adjacent sides. So now I can sum for the forces in the tangential direction. And doing that is equal to the sum of the forces in the tangential direction is equal to... Okay, so let's begin with the reaction in the y. The reaction in the y has the opposite component. So that's going to be sine over 45. Because opposite over hypotenuse is equal to 45 degrees. Now, for our reaction in the x. Now, our reaction in the x is going to be like cosine, because notice how the adjacent side is going towards the tangential. So that means reaction in the x is equal to cosine of 45 degrees, right there. And now for our weight also has an adjacent angle pointing toward the tangential. So we could just say that cosine of theta there. Oh, and something to notice here is how this arrow is pointing downwards of the weight. So it's pointing towards the positive normal, but the negative tangential. And because it's pointing towards the negative tangential, this side here is going to be negative because of that. So just something to notice. And that's going to be equal to our mass times the normal acceleration. The tangential acceleration, which is here. Okay, now we are trying to solve for the reaction in the y and the reaction in the x, but here we have two unknowns and one equation, so we need a different equation, another one, to solve for these reactions, and we do that by summing the forces in the y direction. I mean in the normal direction. The forces in the normal is going to be equal to, now notice here how the reaction in the y is pointing towards the negative normal but the positive tangential, and it's going along the adjacent side, so that means it's going to be a negative cosine of 45 degrees. Now moving on to the reaction in the x, that is going to be, if it's pointing towards going along the opposite, that's going to be the sine. And for our weight now. Okay, our weight also has a sine because, as you can see, this opposite is is parallel to the normal. So that's going to be W sine of theta. And also, do you want to reemphasize again, since this weight is pointing towards the bottom, it is pointing in the positive normal, so that means that component is going to be positive, unlike this one. And this entire thing is equal to the mass times the acceleration in the normal. And recall that the acceleration in the normal is going to be dependent on the velocity squared divided by the radius. Right there. Okay, now I have two equations and two unknowns, and I could solve. Okay, so to solve this, to solve for this, I'm not going to solve this by hand, but I'm going to use MATLAB to solve it. And once I solve it, I end up with this code. This is the code I used to solve for my reactions in the x and the y. And the answer to that is going to be that the reaction in the x is equal to 207.43 newtons, and the reaction in the y is equal to 570.59 newtons. And these are our answers. I just solved for the reaction in the x and the y using normal and tangential coordinate systems. Well, class, this has been my video, and I hope you've enjoyed it. Bye-bye.